Welcome. Today we're diving into the fascinating world of Transformers architecture, foundational technology behind large language models or LLMs. Transformers have revolutionized the field of artificial intelligence, enabling machines to understand and generate human-like language. In this video, we'll break down how Transformers work, why they're so powerful, and how they fit into the broader context of LLMs. Whether you're new to AI or looking to deepen your understanding, this journey will clarify the core ideas and innovations that make Transformers essential in today's language technology. Large language models, or LLMs, have become a cornerstone of modern AI applications, powering everything from chatbots to advanced search engines. Their ability to process and generate text at scale is largely thanks to the underlying transformer architecture. For transformers, models struggled with long-range dependencies in context. The introduction of transformers marked a turning point, allowing LLMs to handle vast amounts of information efficiently and accurately. This scene sets the stage for understanding why transformers are so crucial in the evolution of language models. Transformers are a type of neural network architecture introduced in 2017. Unlike previous models, transformers rely on a mechanism called attention, which allows them to weigh the importance of different words in a sentence, regardless of their position. This flexibility enables transformers to capture complex relationships in language, making them ideal for tasks like translation, summarization, and question answering. Their architecture is modular, scalable, and highly parallelizable, which is why they've become the backbone of LLMs. The heart of the transformer architecture is the attention mechanism. This concept allows the model to focus on relevant parts of the input sequence when making predictions. Instead of processing words one by one, attention lets the model look at the entire sequence and decide which words are most important for understanding the context. This approach overcomes the limitations of earlier models, which often lost track of long-range dependency. Attention is what gives transformers their remarkable ability to understand nuanced language. Self-attention is a specific form of attention used in transformers. It allows each word in a sentence to consider every other word when forming its representation. For example, in the sentence "the cat sat on the mat," self-attention helps the model understand how cat relates to sat and mat. This mechanism is key to capturing the full meaning of a sentence, regardless of its length or complexity. Self-attention enables transformers to excel at understanding context and relationships within text. Transformers use a technique called multi-head attention to further enhance their understanding of language. Instead of relying on a single attention mechanism, they use multiple heads that each focus on different aspects of the input. This allows the model to capture various relationships and patterns simultaneously. For instance, one head might focus on grammatical structure while another looks at semantic meaning. Multi-head attention is a powerful tool that makes transformers highly effective for complex language tasks. Like traditional models, transformers don't process input sequentially. To help the model understand the order of words, transformers use positional encoding. This technique adds information about the position of each word in the sequence, ensuring that the model can distinguish between, say, "the cat sat" and "sat the cat." Positional encoding is essential for maintaining the structure and meaning of sentences, allowing transformers to process language in a more human-like way. Original transformer architecture is built around an encoder-decoder structure. The encoder processes the input sequence and creates a rich representation, while the decoder uses the representation to generate the output. This setup is especially useful for tasks like translation, where the model needs to convert text from one language to another. The encoder-decoder structure allows transformers to handle complex transformations and maintain context throughout the process. The encoder is responsible for reading and understanding the input text. It consists of multiple layers, each containing self-attention and feed-forward networks. As the input passes through these layers, the encoder builds a detailed and nuanced representation of the text. This representation captures not just the meaning of individual words, but also their relationships and context within the sentence. The encoder's output is then passed to the decoder for further processing. The decoder takes the encoder's output and generates the final sequence, such as a translated sentence or a summary. Like the decoder is made up of multiple layers, but it also includes mechanisms to attend to both the input and the previously generated output. This allows the decoder to produce coherent and contextually appropriate text, one word at a time. The interplay between encoder and decoder is what makes transformers so versatile for a wide range of language tasks. Within each layer of the transformer, there's a feed-forward neural network. This component processes the output of the attention mechanism, adding another layer of abstraction and learning. The feed-forward network helps the model capture complex patterns and relationships in the data, making the overall architecture more expressive and powerful. By stacking multiple layers, transformers can learn increasingly sophisticated representations of language. Layer normalization is a technique used in transformers to stabilize and speed up training. By normalizing the inputs to each layer, the model can learn more efficiently and avoid issues like exploding or vanishing gradients. This ensures that the model's performance remains consistent, even as it grows in size and complexity. Layer normalization is a small but crucial detail that contributes to the success of transformer-based LLMs. Residual connections are another important feature of transformer architecture. They allow information to bypass certain layers, making it easier for the model to learn deep representations without losing important details. Residual connections help prevent the degradation of information as it passes through many layers, ensuring that the model retains both low-level and high-level features. This design choice is key to building deep, effective neural networks. Transformers achieve their power by stacking multiple layers of attention and feed-forward networks. Each layer builds on the previous one, allowing the model to learn increasingly complex patterns and relationships in the data. This deep architecture is what enables transformers to handle challenging language tasks, from translation to summarization and beyond. The more layers, the more expressive the model becomes, though this also increases computational demand. One of the key advantages of transformers is their ability to process data in parallel. Unlike earlier models that handled sequences one step at a time, transformers can analyze entire sequences simultaneously. This parallelization makes training much faster and more efficient, especially when dealing with large datasets. It's a major reason why transformers have become the architecture of choice for large language models. Transformers are particularly good at handling long sequences of text. Thanks to the attention mechanism, they can capture dependencies between words that are far apart in a sentence or paragraph. This ability is crucial for tasks like document summarization or question answering, where understanding the broader context is essential. Transformers' capacity to manage long-range relationships sets them apart from earlier models. Transformers are highly scalable, meaning they can be expanded to handle larger datasets and more complex tasks. By increasing the number of layers or attention heads, researchers can build models that are more powerful and capable. This scalability is a big reason why transformers have become the foundation for state-of-the-art LLMs, which often contain billions of parameters. Most large language models based on transformers are trained in two stages: pre-training and fine-tuning. During pre-training, the model learns general language patterns from massive datasets. Fine-tuning then adapts the model to specific tasks such as translation or summarization. This two-step process allows LLMs to achieve high performance across a wide range of applications, leveraging the flexibility of the transformer architecture. Transfer learning is a powerful concept enabled by transformers. After pre-training on large datasets, the model's knowledge can be transferred to new tasks with minimal additional training. This approach saves time and resources, making it possible to build highly capable language models without starting from scratch for every application. Transfer learning is a key reason why LLMs have become so widely adopted. For text can be processed by a transformer, it must be broken down into tokens. Tokenization is the process of converting raw text into smaller units such as words or subwords that the model can understand. This step is crucial for handling different languages, dialects, and even typos. Effective tokenization ensures that the transformer can make sense of any input, no matter how complex. Embedding layer is the first step in the transformer's processing pipeline. It converts tokens into dense vectors that capture their meaning and relationships. These embeddings serve as the input for the attention mechanism, allowing the model to work with numerical representations of language. High-quality embeddings are essential for the model's overall performance and understanding. After processing the input through multiple layers, the transformer produces an output sequence. The output layer is responsible for converting the model's internal representations back into human-readable text. This step is critical for tasks like translation, summarization, or answering questions, where the quality of the output directly impacts the user experience. Masked language modeling is a common pre-training task for transformers. During training, some words in the input are replaced with a special mask token, and the model learns to predict the missing words. This approach helps the model develop a deep understanding of language structure and context, making it more effective for downstream tasks. Another pre-training task is next sentence prediction. The model is given two sentences and must determine if the second sentence logically follows the first. This task helps the model learn relationships between sentences, improving its ability to generate coherent and contextually appropriate text. Transformers can be used in both autoregressive and autoencoding settings. Autoregressive models generate text one token at a time, predicting the next word based on previous ones. Autoencoding models like BERT focus on reconstructing masked parts of the input. Both approaches have their strengths and are used in different types of LLMs. Training a transformer model requires massive amounts of data and computational power. The process involves adjusting millions or even billions of parameters to minimize prediction errors. Advances in hardware and distributed computing have made it possible to train ever larger models, pushing the boundaries of what LLMs can achieve. Once trained, transformers can be used for inference, generating text, or making predictions based on new input. Inference is typically much faster than training, allowing LLMs to respond in real time to user queries. Efficient inference is crucial for deploying LLMs in practical applications, from chatbots to search engines. Since their introduction, many variants of the transformer architecture have been developed. These include models like BERT, GPT, and T5, each optimized for different tasks and use cases. While the core principles remain the same, these variants introduce innovations that further enhance performance and flexibility. ERT is a popular transformer variant that uses bidirectional encoding. Unlike traditional models that read text left to right or right to left, BERT considers both directions simultaneously. This approach allows BERT to capture richer context and produce more accurate representations, making it highly effective for tasks like question answering and sentiment analysis. GPT, or Generative Pre-trained Transformer, is another influential variant. It uses an autoregressive approach, generating text one word at a time based on previous context. GPT models are known for their ability to produce coherent and creative text, making them popular for chatbots, story generation, and more. T5, or Text-to-Text Transfer Transformer, treats every language task as a text-to-text problem. Whether it's translation, summarization, or classification, T5 converts inputs and outputs into text. This unified framework simplifies training and allows the model to tackle a wide variety of tasks with a single architecture. Large language models powered by transformers are used in countless applications today. From virtual assistants and chatbots to translation services and content generation, LLMs are transforming the way we interact with technology. Their ability to understand and generate human-like language is opening up new possibilities across industries. Despite their success, transformers face several challenges. Training large models requires significant computational resources and energy. There are also concerns about bias, interpretability, and data privacy. Researchers are actively working to address these issues, making LLMs more efficient, fair, and transparent. Make transformers more accessible, researchers are developing techniques to improve efficiency. These include model pruning, quantization, and distillation, which reduce the size and computational requirements of LLMs. Such innovations are making it possible to deploy powerful language models on a wider range of devices, from servers to smartphones. Understanding how transformers make decisions is an active area of research. Interpretability tools and techniques help researchers and users gain insights into the model's inner workings. By visualizing attention patterns and analyzing outputs, we can build more trustworthy and transparent language models. As LLMs become more powerful, ethical considerations are increasingly important. Issues like data privacy, misinformation, and responsible AI use must be addressed to ensure that these technologies benefit society. Ongoing research and policy development are essential for guiding the responsible deployment of transformers and LLMs. Future of transformers and LLMs is bright, with ongoing research pushing the boundaries of what's possible. Innovations like sparse attention, adaptive computation, and multimodal models are expanding the capabilities of language models. As these technologies evolve, we can expect even more powerful and versatile AI systems. While transformers are best known for language tasks, their architecture is being applied to other domains as well. In fields like computer vision, biology, and even music, transformers are enabling new breakthroughs. Their flexibility and power make them a valuable tool across many areas of artificial intelligence. The AI community has played a major role in advancing transformer technology. Open-source projects and collaborative research have accelerated progress, making cutting-edge models available to everyone. This spirit of sharing and innovation continues to drive the field forward. Transformers and LLMs are being adopted across industries, from healthcare and finance to entertainment and education. Their ability to automate tasks, generate insights, and improve user experiences is transforming the way businesses operate. As adoption grows, we'll see even more innovative applications emerge. With the power of transformers, AI systems can now deliver highly personalized experiences. By understanding user preferences and context, LLMs can tailor responses, recommendations, and content to individual needs. This personalization is enhancing everything from customer service to online learning. Transformers are increasingly being designed for continuous learning, allowing them to adapt to new information over time. This capability is essential for keeping models up to date and relevant in fast-changing environments. Continuous learning ensures that LLMs remain effective as language and user needs evolve. Transformers are enabling new forms of collaboration between humans and AI. By augmenting human capabilities, LLMs can assist with research, creativity, and decision-making. This partnership is opening up exciting possibilities for innovation and problem-solving across disciplines. To recap, transformers are a groundbreaking architecture that powers today's large language models. Their attention mechanisms, scalability, and flexibility have made them the foundation for a wide range of AI applications. As research and development continue, we can expect even more impressive advances in language technology and beyond. Thank you for joining us on this exploration of transformers architecture in the context of LLMs. As AI continues to evolve, transformers will remain at the forefront of innovation, shaping the future of language technology. Stay curious and keep exploring the incredible world of artificial intelligence.